Welcome to Nature at Home. I'm Tracy, and today we are going to be talking about ice. Water exists in three forms: solid, liquid, and gas. Here we've got a cup full of liquid water. The cup in the front is steaming, producing water vapor, the third form, and we've got a cup of the ice in back. Although water does exist in these three forms, today we're going to focus on ice. So I bet you all can tell me lots of examples of seeing ice in nature. You might go skating on a frozen pond, or you might be into ice fishing. You might just like cracking the thin layer of ice that forms on top of puddles. But we all see lots of ice in nature. So how does the water that we see the rest of the year become ice in winter? Well, all water is made up of molecules. We'll consider them the building blocks, I guess you could say. And when temperatures are higher, those building blocks move around faster. And so you might get steam. Sort of the middle ground of how fast they move and how close they are together is liquid water. But as it gets colder, those molecules have less energy and they move around less, and they start to sort of stick together. At 32 degrees Fahrenheit, 0 degrees Celsius, what we consider the freezing point, those molecules have become sticky enough that they start to form what to us seems like a solid layer. Now there is still motion in those molecules, it's just so little that we can't see it the same way we can in liquid water, and that it still sticks together, creating ice that we can walk and play on, or go ice fishing through. The first property of ice that we're going to take a closer look at involves a little experiment. I've filled this cup with water to the Sharpie line that I've drawn just below the Star Wars, and we're going to go ahead and put it in the freezer and let it freeze and see what happens. Hi everybody, we're back for part 2 of our experiment that involves the properties of ice, and I want us to take a look. Now we froze the ice in our container here. If you'll remember, we had filled it to the bottom of the Star Wars line, and I want you to take a look. I'm just looking for my line here. And now, get this so you can see it. Our ice, instead of being at the bottom of the Star Wars line, let me straighten that out, comes to the top of the line. So what happens is that when water freezes, there's actually expansion. So ice will take up more space than water in a container. In nature, you might think of how this applies to objects that are in, say, a pond. There might be trees around the edge or rocks. The pressure of expanding ice can actually help break apart rocks and cause erosion. It can damage tree trunks if the water's up high. And if you think of man-made structures such as docks, it puts a lot of pressure on them when ice expands, and that kind of thing needs to be taken into account in construction. So while we're looking at our property of the fact that ice expands and takes up more space than water, we're going to now let this container thaw so that I can show you and we can see if we ended up with the same amount of water we started with when we're all done. All right, we'll check back in a bit on this experiment. Okay, so if the first property of ice we looked at, that it expands as it freezes, is important to nature because it can break apart rocks and move trees and change landscape, so it's been part of the natural forces for millions of years, then there's another property that's also really important to nature. So we're going to take a look at that property. Did you know that ice floats? Look at it go. So no matter how much ice there is on top, whether there's just a thin layer, and you may have seen this on puddles, or whether there's feet of ice on top of a frozen lake, it always stays on top of the water. It's less dense than water. The fact that ice floats is important in nature because that leaves all this space underneath that's open for fish and turtles to burrow into the mud and live, and frogs. So there's a number of things that this is their winter home, and they're underneath that frozen ice. If everything froze solid, what do you think would happen to fish? And so again, our second property of ice, that it floats, is very important to the natural world. So we've looked at the property of ice, that it expands when it freezes and that it floats. A third property of ice, something I think we're all familiar with, is that ice is slippery. But why is it slippery? I mean, we know that it is, but did you ever stop to think about what causes it? Well, it turns out that scientists know that it is too, and they've thought about it, and they still aren't quite sure why. For a long time, everyone thought that when an object, your foot, a skate, the runner of a sled, or maybe the belly of a penguin doing a penguin slide, came into contact with ice, a thin layer, like too thin for us to see, was melted, and this allowed us to glide across the surface. After all, we all know how slippery it gets when there's water on top of the ice. Well, this is still widely shared by many people. Science has shown that there are a lot of limits to this theory, and it doesn't quite explain why all ice is slippery. So other theories have started to emerge. Another one has to do with the molecules that we talked about earlier, those building blocks. So imagine the building blocks are all stuck together in layers forming your ice. But the ones at the top are only bonded on the bottom. They're loose up top. There's nothing above them holding them in place. And so the theory is that those top molecules are sort of loose and can move about. So again, on a microscopic level, there's a layer there that allows us to glide on top of the ice. This theory has some followers, but still hasn't quite explained how ice is slippery at all temps and conditions. A third theory has to do with friction, that ice melts when it's rubbed by another surface. And again, we're talking a microscopic melt, not flowing water that you can see. However, this theory also doesn't account for all things, like why is ice slippery even when an object is still upon it? So research into the slipperiness of ice continues, but most people currently seem to believe it's a combination of all of these factors that makes ice slippery and means that we land on our butts when we're not being careful. But I like to think about this friction theory a little bit more because it plays into our next question. We know ice is slippery, but is all ice equally slippery? And the answer is no. I bet you probably already guessed that on your own. And part of the reason that not all ice is equally slippery has to do with friction. Friction is the resistance of one object moving against another. So imagine you're in your sock feet running, ready to do a slide across the floor. If you're going to slide on hardwood, you're going to get a nice long slide and cheer at the end. If you try to do the same move, sliding your socks on a carpeted floor, you're probably going to fall down. That's because your socks, cloth on cloth, socks on carpet, have greater friction than socks on a smooth surface, less friction. And less friction means you're going to glide better. So you're watching some sledding videos now while I talk, and let's see how well our sled is going down the hill. Now, the cardboard of the sled is kind of like socks on your carpet. It doesn't have the best slide. It has more friction, so our sled's not getting going very fast. Also, the ice here is very bumpy. Smooth ice is more slippery than bumpy ice. And that has to do both with friction and how sort of the edges of the sled catch on its way down. That's also why you'll see Zambonis fixing the ice at skating rinks to make a better surface for figure skaters and hockey players. The Zamboni makes for smoother ice, which is more slippery. Finally, I want to end with a fun experiment that kids and parents can do together at home. You may have heard that hot water will actually freeze faster than cold water. We want to find out if we can determine if that's true. The supplies you're going to need a paper and pencil or pen so that you can write down the times that you started and when your ingredients have frozen. Or a stopwatch, which could also be on your phone. Just make sure it's one that lasts a long time because water will take hours to freeze, not minutes. You're going to need 2 containers, one for your hot water and one for your cold water. You want to make sure that you put the exact same amount of water in each. So I've taken a ruler and marked the spot where I'll go to the bottom of my marker line on both of my containers. You're going to need cold water. Mine happens to be straight out of the tap, but I let it run for a while to get nice and cold. And then you're going to need hot water. I've heated up some water in my kettle. If you have a thermometer, you can use that to determine the temperature of the water before you started. In this case, let's see what we've got. My cold water is going to be about 55 degrees. Let's see what my hot water is. And remember, if you're using hot water, you have to be really careful and get mom and dad's help. My hot water is about 206 degrees. So I'm going to go ahead and I'm going to get my cups ready. I got a little too much in that one. So again, want to make sure they're even to the bottom of my line. And then I'm going to go ahead and put those in the freezer. And I'll check back with you in the comments later and let you know what happened. But if you do this experiment at home, I'd love to hear what you found out. And later on, I'll also post a science of if this is true or not and what really happens. But I want to give you a chance to do your experiment first. So thank you for joining us today and learning about how ice is formed and how it plays a part in nature. Hope you enjoyed it, and I hope you'll try some of the activities at home and see what you think. We want to thank all of you for joining us each day, and we also want to thank the New York Power Authority who funds our facility and programs. And finally, until tomorrow, I'm going to leave you with some clips of how our staff like to enjoy ice. If you like activities on ice, please feel free to share with us in the comments what your favorites are and a pic if you have one.